IO modifiers. What the heck are IO modifiers? Not to worry. This video is going to cover everything you need to know about the basics of IO modifiers, okay? So have some patience and sit back and relax and learn about IO modifiers, okay? Input, output modifiers, all right? So we have our inputs and our outputs, and we can use these IO modifiers, which reside in the menu. We can use these to modify the data that's coming in or going out of our components, okay? Now, oftentimes these modifiers are on the input, on the output, are the same, but not always. There's sometimes a certain extra modifier on the input or the output, okay? So we're going to go through sort of the standard list, and then we're going to look at some modifiers that come up less often, but are still very important. We're also going to look at some components that actually do a very similar job to IO modifiers, okay? And we can kind of use those as a reference point to help us understand these IO modifiers, okay? And then we're also going to go through a few examples of each modifier, each main modifier, okay? So let's get started. First of all, we have this kind of standard list. Now, there's no real kind of standard modifier list, but this is the list that will show up most often. So I'm kind of calling it a standard list, all right? These are the most common modifiers. So we have principal, reverse, flatten, graft, simplify. These are all affecting the data structure in some way. And I'm going to explain, I'll show you that in the demo below. And we have the same modifiers on the output. This is the extrude component. You know, it's a basic component. And I've actually put it on here twice because if you look in the direction input, we actually have 2 extra IO modifiers. And we have Unitize and expression. So first of all, expression is going to show up almost any time that we have a number input, some type of input with a number or a vector or something with some type of number associated with it. We're going to have an expression IO modifier. And what we can do with the expression modifier is we can type in some type of mathematical expression that will affect the input or the output. So x is the value that's coming to the input, and then we can put any type of mathematical expression. X times 2, x divided by 2, plus 4, whatever. So this is super useful. I use this all the time, and you're going to see it in a lot of my videos. So what is the Unitized modifier? The Unitized modifier is all it's doing is, because this is a vector input, a unit vector is a vector of 1 unit length. So a unit vector would be a vector with a defined direction, but the amplitude would be a unit of 1. And if you put in a bunch of vectors, or just if you put one vector or multiple vectors into this input, the Unitize IO modifier will convert all the vectors into unit vectors. So single unit vectors, okay? Or it will be if you're combining vectors into if you're adding or multiplying vectors, it will still convert the final vector into a unit vector. Okay, what else do we have here? Again, I will go through these IO modifiers, but they're a little bit I don't really want to try to explain it. I'd rather show it in the demo. So I'm just going to briefly go over these other modifiers, and then we can go through the demos, okay? The demonstrations. So a degrees modifier is pretty straightforward. Any input that requires an angle number, an angle value, is going to have a degrees modifier. And the reason for that is because by default, all of the components are working in radians. By default, the program basically operates in radians. So if you want to work in degrees, you kind of just select degrees to change your preference to working in degrees. Okay, and we can see that here. So we're actually that's what this component does. It converts from radians to degrees, and it's doing the same job. Okay, so if we were to measure like a vector or something, if we were to measure the angle of this vector, it's going to give us our number in radians. See, it says in brackets in radians. So we could actually change. We can't change the output here, so we would have to change the input to degrees. Sorry, what I mean is this is in radians, so you leave it as radians. But if you had a different input, if you were using a number slider and you wanted to use degrees, then if you want this to be 100 degrees and not 100 radians, then you change it to degrees. Okay. So the Re Parameterize Modifier. Ooh, okay, I almost tripped up on that word. Got it. Yes. So the Re Parameterize modifier, what it's doing is it's changing the domain of a curve. This will always show up when you have a curve as an input or a surface, and it's changing the domain of the curve or surface to 0 to 1. Pretty straightforward. I'll show you that in the demonstration. Okay, invert multiplier is changing the Boolean value. It's just flipping it. If it's true, it's going to be false, and if it's false, it's true, and it will do that no matter how many items are in the list. It's going to change all of them. It's going to flip all of them. It's going to invert. And so another thing to note is that any of these math components, they don't have an expression modifier, which, to be honest, I wish they did have an expression modifier, but I understand why they don't, because if you're going to put an expression into a math modifier, a math component, you might as well just use an expression component right here. So if you wanted to add, if I wanted to go x plus x divided by 2 times b, if it was a divided by 2 times b, I could just use an expression and I can add more inputs and just use the expression component to do that. Okay, so like I said, most components with a number input, like for example this angle, it's gonna have an expression modifier, but not these math components. They don't have it. Okay, it's not a big deal. So let's take a look at some demonstrations. So we'll start with principal. Okay, so principal is that first IO modifier in the list of standard modifiers. I don't have. Oh, do I have a? Okay, this is the example. Here we go. So let's say this is like a plot of ground. This brep is a plot of ground. We have these tiles, and we want to kind of spread some patches of grass or patches of flowers onto this grass. What we can do is create a 2D random distribution of 2D points, and we can project those points onto that brep. Now, some of them are going to miss, right? Some of them are not going to hit that surface when we go to project. And what that means is we're going to end up with empty branches. We have lots of null branches because any place where a point missed, we have an empty branch. Okay. After we've grafted this. Okay. We'll talk about that. We've grafted this data. Now we have these empty branches. And maybe the reason we grafted it maybe is because we want each point to be in a separate list, because maybe we want each point to maybe we want to multiply these points and create sort of a patch of flowers or something like that. So we want each point to be in a separate list so we can kind of operate on them separately, right? So we've grafted it, and we have the dash line, meaning that it's grafted data, but now we have these empty lists, these null items. And we're going to take the clean tree component to clean this up. And what we've done here is we've said remove null items from the tree, true. What else do we have? Remove invalid, remove empty items, empty branches, that is. And what we're left with is this. And if you look closely, you'll see that we have missing branches, 0, 1, 2, 3, 4, 5, 6. So 3, 4, 5 is missing, right? So 3, 4, 5 is missing because this clean tree component removed those branches where we had these null items. See, 3, 4, 5. It just removed them, but it saved the path structure. Okay, and maybe that's important. Maybe we need to save the path structure for something that we're doing later on. Maybe we need to save that information. And up here, and so I'll get back to that in 1 second. Let's take a look at this is the principal IO modifier here. So we'll get to that in 1 minute. What's happening here is we have these random circles, these random radius circles, and we've also grafted it. So we have a bunch of circles of random diameters, random radii from 1 to 10. Okay, and we have the same number of them, of circles, as we do points, because we want completely different circles. So we have this list, but this list is actually, it has the same number of branches. Okay, 67 branches, 67 branches coming from this clean tree component. So we have 67 points, and we have 67 circles. So it has the same number of branches, but if we look at the last index number, the last branch number, sorry, we actually have more branches here. And remember, that's because we took these initial points, and and we removed all the null items. So we still have the same number of branches, but we have a whole bunch of skipped branch numbers. Okay, but let's say we wanted to retain this branch structure for some reason, because we want to maybe use this later. Want to use that data later. We want to retain this branch structure. We can do that if we want to using the principal IO modifier. So I have that turned on, and now what happens is it uses this input stream as the priority for the tree structure. So when we plug this into this param viewer, now we actually see 99 branches. Okay, so it matches the original path structure. Okay, so that's what the principal IO modifier does. It matches the tree structure. Okay, so that's the basics of principal. So let's take a look at the next IO modifier, reverse. Okay, so reverse takes place in most standard lists. We also have a reverse list component right here. So let's take a look at this example over here. Let's see. We have a collection of circles, and I can modify these circles, and you can see that this series down here is going to update depending on, it's going to sort these circles based on biggest to smallest. Okay, if I modify them, it's going to automatically resort them. Okay, and so basically what's going on here is what we're doing is looking at the area of the circle, and we're sorting the circle using the keys in the sort list component, and then we are using the keys to sort the centroids, the center of the circle, right? And we're using the B values to sort the actual circles themselves, and then we can throw it into this definition that calculates the distance between the circles and aligns them and places them in order. So, but in order to get from biggest to smallest, we actually had to do reverse list, because reverse list, I'll show you here, or sorry, sort list to component always goes from smallest to biggest. All right, always from smallest to biggest. But if we use reverse list, we can reverse the direction of that sorting order. So reverse list goes from in this case, reverse list could be used to go from biggest to smallest. And we've done that here because if we take reverse list off of these two components, now we go from smallest to biggest. Okay, so that's what we can use. That's one example where we can use reverse list. Awesome. Okay, let's go to the next example. Flatten, graph, simplify. I've put these into the same demonstration because this demonstration has all of them. Lucky us. It's awesome. So we can see we have flatten tree component here, graph tree, and simplify tree. These are all found in the sets subcategory. Let's see what's going on here. So what we've done is we've created this hexagon grid, okay? And we have this curve. Let's see where that curve is. This is the curve. And we want to create points based on where this curve is intersecting with these hexagons. Because let's say eventually we want to trim them or something like that. We need to know where they intersect. And but we want to know both intersection points. Okay? So I actually want to know where. So you'll see here we have these lists with 2 items. We have 2 items in each list, and that's actually because it's calculating a point for the intersection on each hexagon. These are separate hexagons, right? These are not separate curves. So I should highlight that actually. We'll take this thing here. Let me just show you. Okay, so we can see here, right? We have full hexagons. So there's going to be a lot of overlapping curves, but that's fine because we want full hexagons when we're doing this. Okay. So, and so what I was saying is that this is a full hexagon, and we need to see a point of intersection, and there's always going to be 2 points of intersection for each hexagon. So this hexagon here is going to have 2 points. This hexagon is going to have 2 points. And we want to maintain that data structure because maybe we need to split each hexagon independently. Okay. And so let's see how this is working. We've created our hexagon, our honeycomb structure. We have our curves. And when we, first of all, let's take a look at this. Let's take a look at the flattened tree, IO modifier. And now I'm using the flattened tree component, but you can just pretend that I'm using the flattened tree modifier because it would have the exact same result. And we can actually have a simplified component. Well, we can use a simplify and a flatten component. It's kind of redundant. We can also use a simplify and graphed component. So these two can be on at the same time. Graphed and flatten are fundamentally opposite of each other. Okay, so those cannot be on at the same time. So we have the simplified component on. Let's take a look at what it looks like with and without the simplified component. So this is our, this is our initial honeycomb structure. And it's automatically grafted, actually. Okay, so that's what it looks like by default. And actually, so I just turned the simplify component off, and what the simplify component does is it simplifies the structure of the tree. And so here you can see our path is 001, 000, 001, 003, and it's just going to go up. It's just going to be 0014. It's redundant. There are cases when you don't want to simplify and you want to maintain that tree structure, but in this case, it's not necessary. And this is what it looks like as a visual representation of that tree structure. This is what it's looking like. So we have this root, the root of our tree, and it's going up one level, and then going up another level. Okay, so this path structure is redundant and it's unnecessary, and it's not necessary to simplify it, but it's usually good practice if you don't need it to be if you don't need that tree structure. I find it to be helpful to simplify it just for the sake of clarity. So I'm going to simplify it, and we can see how that tree structure simplifies right down to the most simple tree structure, essentially, other than a flattened tree structure. And now when we look, our paths are actually single digit paths. Okay, so that's what's going on here, because 0, 1, 2, 0, 1, 2, but if it's not simplified, we have these levels. Okay, these levels until we make it to our branch. So that's going to be simplified. All right, that's what simplify is doing. And we'll obviously look at more complex examples in later videos. Okay, what happens? What does the flatten tree component do? Okay, again, this flatten IO modifier will do the same thing as the flatten tree component. So let's see what that looks like. It's actually one giant list. Okay, just one giant list of items. And if we plug that into our param viewer, that's it. There's one branch. It's just 0, one branch, one list. And so that's what flatten is doing. But let's be very clear on what's going on here. It's taking each list and it's moving them all down to one branch. So it's not deleting the items. It's not deleting the data on all the branches. It's just moving them all down to the first list with the path of 0. Okay. So we have 254 items. It's the same amount of data with just a different tree structure. Okay, so this item is the next item after this one in this new flattened list. Okay, and our index numbers continue going up from 0. So now that we flattened the list, what does that actually entail in the model? Well, if we plug in this original hexagonal series of this honeycomb structure, this series of hexagons, we're going to use this tree branch component. And the tree branch component is what we can use to identify one of these tree branches. And so right now we have our path is 0, so we're on the 0 tree branch. And if we change the tree branch, we can change. If we change the path, we're gonna change which branch we're actually going for. Okay, and if I click on this, if I preview this, now look, check this out. So we can see that hexagon down there because we're on path 0, branch 0, tree branch with a path of 0, and our index number is 0. And what if we increase the path number? Well, let's try it out. Okay, so now we're moving across in the x direction. Okay. And so the paths are, so we can start to see how the branches are being constructed in the actual model. And if we move our list item, we're actually going to be going in the y direction. All right, so if our y direction is in an index of 5, we change our path, we're going to go across like this. Okay, so what you can see now is that when you're looking at these branches, And when you're looking at these lists, what's actually happening is that each one of these rows, each one of these columns, I should say, is a separate list. So this is 0, 1, 2, 3, 4, etc. This is 0, 1, 2, 3, 4, etc. But the branch is different. So the branch is going 0, 1, 2, 3, 4, 5, right? So each one of these items is related to one of these items. And then in the next branch, branch 1, these items are in the second column, all right? So that's what's going on there. And that's how the hexagonal component, that's how it defaults. It's defaulted to organizing the geometry in that way. But I don't care about the structure right now. So I'm just going to flatten it. I'm just going to kill the whole thing. I'm going to chop down the whole tree. And I just want one branch. And now that it's one branch, if I plug that into my list item, what it looks like, what it looks like is this. Now our items are all in one list, and it's just going this way and then back down to here, back down to here, back down. Okay, so it's just one giant list. And that's fine because we're just looking for the intersections between this curve and this hexagonal structure. There's definitely other cases when we would actually want to do the opposite, and we'd want to graft the structure. Okay. So okay, so if we so let's take a look. What would that look like if we were to graft this structure? If we flatten it here, and then if we actually use this IO modifier and we grafted it on the output of the flattened tree component, now we actually have a whole bunch of separate lists. Okay, separate lists of independent hexagons, right? So each one of these hexagons is in a separate list, and that's what the grafting component is doing. It's actually splitting up all the data into separate branches. And we actually already saw that in the first example when we took these projected points, we grafted this, right? We had these points all in one list, and then when we projected the points, we grafted it into separate lists so that we could manage them in that way. So we could manage them in separate lists. There's a lot of advantages to that. We'll see how that why you'd want to do that in a lot of the videos that we're going to be working on. A lot of the stuff that I want to teach you guys is very kind of data heavy. You have to have a decent understanding of kind of the data management, but I'm not a programmer, and I was able to kind of figure it out as much as I needed to. So don't worry, you don't have to be a programmer and understand data paths super well to be able to do this stuff. You just kind of have to learn how you want to be able to visualize it yourself. All right. So what else is going on here? We talked about flatten, graft, simplify. We over here we have we found our intersections. Okay, we have found the intersection point between this curve and the hexagons, and we have a whole bunch of empty lists, empty branches. So we're going to use the clean tree component again to just knock out those empty branches, just cut them off. And now you can see that our you can see now that we have okay, so what we've done here is we've figured out which branches have data in them. After we clean them, we use the param viewer to export basically which branches have data in them, and then we use the deconstruct path to turn those branch numbers into number values. And then we've taken this original list, this list here of hexagons. This is all the hexagons. We've taken that list and we've isolated only the hexagons that are intersecting with this curve. Okay, so maybe we wanted to just use, maybe if we were, you know, doing some landscaping or tiling or something, we could use this curve to kind of generate the rough shape of these tiles, these hexagon tiles or stones. And but we don't want to cut them, maybe. So this is one way to do that. We're just isolating only the isolating the tiles that are making that intersection. Okay, so that's an example of, you know, how we could use this strategy. All right, let's keep going. I think we covered that. Degrees. We talked a little bit about degrees previously. This is a super simple example. There's not too much to be said here. We have like 4 components on here. We have this rectangle. Of course, we can change the size. We have our point of rotation. It's also acting as a plane, the base of the plane. And we can rotate. I'm using this control knob to make our rotation, just for fun. And but you'll notice our units look like they're in degrees, because when I'm 359 degrees around, when I'm 359, I'm obviously 359 degrees around as a rotation. So, and that's because we have the degrees IO modifier on. All right. Let me show you. I didn't mention that. Where's expression? I used an expression somewhere, and I forgot to mention it. Oh, here's the expression. Oh, we also used degrees here in this right trigonometry component. So this component calculates the lengths or the degrees of a right angle triangle, and we actually use the degrees modifier in here because I was inputting a degrees. I was actually just typing it in here in set number. Here, 30. And I use the degrees expression modifier to make that 30 degrees, not 30 radians. Right. So we also use the expression modifier in this hexagonal component. Using expression to basically, I'm not going to get into it too much, but basically, you know, this hexagon is determined by sort of the radius of the hexagon, so from the center point to the edge. And I'm using some math to figure out how to make the hexagon, the honeycomb structure, fit this rectangle. So because because the size is from the center to the edge, if I take that number and I multiply it by if I take the width of this box and divide it by the number of, by this distance, I'm going to get twice as many honeycombs. So I'm going to use an expression in here to take this number and divide it in 2. So if I didn't have this expression, it's x divided by 2 plus 1, it would look like this. It would be twice the size, because this is specifying the number of hexagons in the grid. So I'm just going to use this x divided by 2. I'm just going to add a 1 just for fun. Okay. And that's how the expression is working. So we're taking this number 31 and we're turning it into 17. All right. It's going to round this one automatically because it needs to be. Okay. So we talked about expressions, we talked about degrees, we're talking about Re Parameterize. All right. So Re Parameterize. This one is I'm not sure how often you're going to come across this. I've used it a few times for sure. One thing to note is that the Re Parameterize curve component is not native to Grasshopper. I don't think there is a native component in Grasshopper. So this component is actually in Pufferfish if you want to check that out. All right. So Pufferfish, Re Parameterize curve, you can check that out if you want in Pufferfish. So what does it do? Re Parameterize curve. We have this curve here that we've drawn in Rhino, referencing this curve. And if we check out the domain of this curve, something weird, 0 to 666. If this curve is not reparameterized, it's gonna when we're trying to find, let's say, the parameter on the curve, the parameter is it's a parameter on the curve domain. Okay, so we're looking for a parameter on the domain, and since our domain is 606, we're not gonna get very far. You can see that point is barely moving because we're moving from 0 to 1 on that domain, and we could change this number slider to match this domain, but it's not really parametric, because if we were to modify this curve and we made it longer or shorter, it's going to change the domain of the curve. So we might want to always have that curve reparameterized to the same domain, and what that same domain is 0 to 1. So let's take a look. So what happens here, so our curve domain is 0 to 606 with the reparameterized curve. Let's take the output from here. Now you can see it goes 0 to 1. All right, and that's going to do the same thing in here when you go to reparameterize. Boom. Now 0 to 1 makes it across the entire curve. It's going to place a parameter anywhere along that curve. Okay, and we can do the same thing with the surface. A surface also can be reparameterized. Okay, and the difference is, well, it's not really any different. It's just that a curve has a domain in one dimension, and a surface has two domains. A domain in each dimension. It's two-dimensional. Okay, there's a domain in the x and a domain in the v, and a domain in the y, the w. Dimension on the u and the v. So it's going to be a 0 to 1 domain on the u and the v dimensions. Okay, had a brain fart there. All right, invert. This is the last one. This is the last one. It's a very simple concept. You guys are gonna pick it up like nothing. Invert. Whoa, nice. We have a cool example though. I'm trying to keep you guys awake with this crazy example. You might have already seen this actually in a previous video. We have a bunch of points. Let's see, what did we do? We have kind of created an attractor script, and the attractor script basically takes this point and we're generating all the black points. We want the black points to be near that. We want to create a gradient from black points to white points, depending on how close it is, depending on the proximity to this attractor point. Okay, so we're always going to have a higher percentage of black points near this attractor, and all the white points are populating away from the attractor. And so, let's see. Well, basically what we're doing is the smaller than component is determining which ones are true and false. And I'm not going to go into how this attractor script is working. We'll definitely talk about that. You can definitely find an attractor script video on my channel if you're interested. And so we have these true, false, true, false. Anything that's false and true and false is determining whether it's black or white. We have this cull pattern component. So this pattern is determining which ones are being culled, basically. So again, a culling component deletes certain items, right? So if I take that out, so this cull component is taking certain items and it's culling them, so it's deleting them from the list. But you'll see that basically this other culling component, if we hide this other culling component is culled the opposite items. So we have this true, false, true, false, true, false, whatever pattern. It's not consistent, but we've used the call pattern component, but these ones are picking up different points. These ones are deleting different points than this one, right? And it's because of this invert modifier. So what does that look like? Well, we don't have an invert component. There is an invert component from pufferfish, but we can also use the component called gate not, which is native to Grasshopper. So what does that look like? Well, look, check this out. We have false, true, false, false, true. Okay. And what if we plug in the gate not? Okay, so this is the original one, false, true, false, false, true. Gate not is now true, false, true, true, false. So we've just flipped these true and false operators, such that it's gonna call opposite list items with these two components because we have this invert IO modifier turned on. All right, so we get whites, we get white here, we get black here, and that's how we get the that's how we get them to agree with each other, get along, and they've just decided which ones are on and off. And we create that gradient, right? Whee. Yeah, this stuff is fun. Okay, anyways, stop playing around. Quit playing around. Okay, here we go. That's the basics of. I think we covered all the basics of IO modifiers. This file I think will be available for download somewhere. So maybe check the description. Hopefully, I'll have it up somewhere by the time you're watching this video. And I hope that helps. If you have any questions, I'd love to address them. I'd love to hear what you guys are thinking about all this stuff. So throw your questions at me, throw your feedback, good, bad, whatever. Love to hear it. All right, guys. I'll see you in the next video.